Tonight, we're going to look at a map of the universe that should not exist. While most people were focused on its pretty images, the James Webb Space Telescope was quietly doing something far more radical. It was drawing the most detailed 3D map of the early cosmos ever made, layer by layer, galaxy by galaxy, time slice by time slice, reaching back to just a few 100 million years after the Big Bang. On the surface, it looks like familiar deep space, faint smudges, tiny arcs, distant galaxies frozen in Webb's infrared gaze. But buried in that map, hidden in the statistics and the redshifts and the subtle clustering of light, scientists have found a colossal structure that should not be there at all. A wall, a filament, a kind of embryonic spine of the cosmic web, appearing long before theory says the universe had time to build it. The standard cosmological model says the universe grows like a slow, patient architect. Tiny fluctuations in the early plasma grow into galaxies, then groups, then the vast web of filaments and voids that link the visible cosmos. It predicts when those structures should emerge, how massive they can be, and how the invisible dark matter scaffolding guides everything. But this new map from Webb points to a region tens of millions of light years across, packed with galaxies and dense threads of matter, at an epoch when no one predicts such complexity. No one expects a fully sketched skeleton so early in the story. To grasp how shocking this is, hold out your hand at arm's length. Imagine a single grain of sand resting on your fingertip. The tiny patch of sky that grain covers is all Webb needs to reveal thousands of galaxies stretching billions of light years deep into time. Within that microscopic window, scientists have discovered vast walls and filaments that rival the largest structures in the modern universe. A speck of sky, a structure spanning cosmic oceans. This is the hidden skeleton of space. Cold gas, dark matter, and young galaxies tracing out a web that seems to have formed too fast. It appears in Webb's deep field surveys, JADES, SEERS, Cosmos, Webb, as a pattern you cannot see with your eyes but can read in the redshift map. It forces astronomers to quietly ask a dangerous question. Have we misunderstood the first billion years after the Big Bang? If this structure is real, the implications reach far beyond one patch of sky. It could mean that the framework behind dark matter, dark energy, and the entire history of cosmic evolution has missed something fundamental about how the universe builds itself. It challenges the limits of our simulations, the timing of inflation, even the way gravity sculpts matter on the largest scales. By the end of tonight, you're going to understand how Webb drew this impossible map, why this hidden structure is shaking cosmology, and how to look at any deep field image and mentally see the 3D cosmic web behind it. Before we get started, remember, maps do not just show where we are. Sometimes they reveal that the territory itself is not what we thought. Now, let's begin. Webb's map was supposed to be a confirmation, a high-resolution beauty shot of a universe scientists thought they already understood. Instead, it looks like someone hit fast forward on cosmic history. In the standard picture, the early universe is nearly smooth. Tiny ripples in density, stretched by inflation, slowly grow under gravity. Over hundreds of millions of years, they turn into filaments, then walls, then full-blown clusters of galaxies. Gentle at first, gradual, predictable. But when the James Webb Space Telescope stares deep into space and far back in time, that slow-motion story starts to crack. Across surveys like JADES, SEERS, and Cosmos Webb, Webb is drawing the most detailed 3D map of the young cosmos ever made. The expectation is simple. At very high redshift, the cosmic web should still be faint, its skeleton barely traced by a few small galaxies. The reality? Webb is finding overdense walls and filaments already spanning tens of millions of light years, at epochs when the universe is less than 1 billion years old. No one predicts that level of clumpiness so early. Along those filaments, the mission keeps running into proto-clusters, crowded neighborhoods of galaxies at redshift 5, 6, even 7, where simulations said there should mostly be scattered dwarfs. Some of these regions look like the seeds of present-day galaxy clusters, forming far ahead of schedule. Right next to them, ultra-massive galaxies appear with stellar masses rivaling the Milky Way, yet shining when the universe is only a few 100 million years old. Designed for a slow build, the cosmic construction project seems to have skipped stages. Then there is the hidden population. Webb's infrared eyes reveal swarms of faint, low-mass galaxies that Hubble missed entirely, tucked into the dark gaps of older maps. They fill in the cosmic web like fog, revealing laser beams, and they change the math on how fast structures can grow. Spectroscopy adds another shock. Evidence of cold gas channels, narrow rivers of pristine hydrogen funneled along filaments, feeding young galaxies more efficiently than standard models allow. Gravitational lensing turns the tension up further. By measuring how background galaxies are distorted, Webb is tracing invisible dark matter scaffolding that seems denser and more sharply defined than LCDM. The leading dark energy plus cold dark matter model comfortably predicts at these times. The observed clumpiness, the sheer amount of structure, pushes against the boundaries of a model that has otherwise explained the expansion history, the cosmic microwave background, and the large-scale distribution of galaxies. Tonight, we're going to treat these anomalies as 7 distinct shocks: overdense walls, early protoclusters, ultra-massive infants, hidden faint galaxies, cold gas channels, dark matter skeletons revealed by lensing, and the deep tension with LCDM tying them all together. By the end of tonight, you're going to understand how each of these discoveries doesn't just tweak a parameter, but challenges the timeline of structure formation and even our assumptions about dark matter and early expansion. If the universe built its skeleton far faster than expected, what else about the cosmic blueprint is wrong? And what happens when we follow that hidden structure to its most extreme example in Webb's map? And that question is exactly why this channel exists. This space isn't for people who only want a new cosmic wallpaper. It's for people who look at those deep, glittering fields and immediately ask, what does this actually mean for physics, for history, for the story of how a solar system like ours appears on one tiny filament of an invisible web? If that's how you think, you're in the right place, because JWST's new map isn't just a prettier version of Hubble's greatest hits. It is a direct test of the script scientists have been using for decades. From the first fraction of a second after the Big Bang, through inflation, through the slow growth of dark matter halos, to the moment planets and oceans and biology emerge, there is a standard narrative. Tonight, we're going to hold that narrative up against Webb's data and see where it bends. Think about what this map actually is. Deep field surveys like JD's, SEER's, and Cosmos Webb aren't just photographs, they are 3D time machines. Each redshift is a timestamp. Each faint smudge is a galaxy only a few 100 million years old. When those smudges line up into walls and filaments tens of millions of light years long, far earlier than LCDM models predict, the universe is quietly saying, your blueprint is incomplete. No one expects a single telescope to rewrite cosmology on its own. No one predicts that one patch of sky will overturn the consensus. But when different Webb fields keep hinting at the same hidden structure, and when those structures seem too massive, too organized, too soon, absolutely no one anticipates the luxury of ignoring it. The question becomes, are the models wrong? Or is there something about the way we're seeing the boundary between light and dark matter that hasn't been understood yet? Before we get started with the next layer of that puzzle, a quick request. If long, carefully researched dives into missions, maps, and the invisible architecture of space are valuable to you, take a second to like this video or subscribe if you haven't yet. It's a tiny action on your side, but it tells the algorithm there are more curious minds out there who want this level of detail, and it directly supports spending weeks on episodes like this instead of quick, shallow overviews. Now, let's begin the next phase with a promise. The rest of this video stays locked on the science and the story. No sponsor detours. No extended self-promotion. Each segment will build on the last, from what the standard model says the cosmic web should look like, to what Webb actually discovered, to how future missions like Euclid and Roman will test whether this hidden skeleton is real. Because to understand why this new map is so shocking, the next step is simple. Now, to understand why this new map is so shocking, we have to rewind to what we thought the universe looked like before Webb turned the lights on. So, before Webb turned the lights on, the cosmic map already looked impressive. On paper, it seemed complete. In practice, there was a glaring blank space right where the universe's skeleton should be. Now, let's begin with the old map. For decades, galaxy redshift surveys were the workhorses of cosmic cartography. Projects like the Sloan Digital Sky Survey measured the positions and redshifts of millions of galaxies, mostly in the relatively nearby universe, out to a few billion light-years. Plot those galaxies in 3D space, and a pattern emerges, not a random scatter. A foam-like lattice of filaments, walls, and vast empty voids, tens to hundreds of millions of light-years across. The local universe looks like a frozen splash. Galaxies flow along filaments, pile up in great walls like the Sloan Great Wall, and avoid the dark cavities in between. By the end of tonight, you're going to understand that this cosmic web is not just a pretty pattern. It is the large-scale structure that any successful cosmological model has to reproduce. But those surveys were looking at the universe in its adulthood. To go back toward its childhood, scientists pushed their space telescopes to the limit. This is where Hubble comes in. With the Hubble Deep Field and Ultra Deep Field, a single patch of apparently empty space was stared at for days. The result was a cityscape of galaxies stretching back more than 12 billion years. There was a catch. Hubble is optimized for optical light. At extreme distances, that light is stretched by cosmic expansion into the infrared, and only the brightest, most massive early galaxies still peek through. The faint, low-mass galaxies that should trace the thin threads of the young cosmic web remained invisible. The web's delicate filigree was missing. The standard picture tying this all together is the LCDM model, cold dark matter plus dark energy. In this framework, the early universe after the Big Bang is almost uniform, with tiny fluctuations in density at the level of 1 part in 100,000. Over billions of years, those ripples grow under gravity. Dark matter collapses first, forming a hidden scaffold. Gas falls in, stars ignite, galaxies assemble, and the web slowly sharpens into the structure mapped by Sloan. Before we get started with the web, notice the gap. On one end, there is the cosmic microwave background, a baby picture at 380,000 years old. On the other, there are detailed 3D maps of the nearby universe today. But the first billion years, the era when the dark matter scaffold was pulling in gas, when the first filaments, walls, and proto-clusters were taking shape, was mostly blank. No one predicts a mission will just leap over that missing chapter. James Webb was built to do exactly that, to push beyond Hubble into the infrared, to turn that blank band on the timeline into a detailed 3D landscape of the young universe. Tonight, we're going to see what happens when that new map refuses to match the script, and absolutely no one anticipates where the cracks in our model start to appear. To see why that new landscape is so shocking, you first have to see how the map is drawn in the first place. How do you chart a universe you can't touch and barely see across tens of billions of light years of space and time? Now, let's begin with the quiet engine behind almost every cosmic distance in modern astronomy: redshift. As the universe expands, it stretches the space between galaxies. That stretching doesn't just move planets and systems farther apart. It stretches the light itself. Waves that left a young galaxy in a brilliant ultraviolet blaze arrive here as deep infrared, their wavelengths pulled longer, redder, colder by the expansion. Measure how much that light has been stretched, and you measure how long it has been in flight. A small shift means a nearby galaxy, seen in relatively recent cosmic history. A huge shift means the light left when the universe was only a few 100 million years old. By the end of tonight, you're going to understand that every redshift is not just a number. It is a timestamp, a look-back coordinate that pins a galaxy to a specific chapter in the universe's story. But redshift is not read off a color wheel. Scientists need something more precise. That's where spectroscopy comes in. Take the light from a galaxy and spread it out into a spectrum, and it stops being a smear of glow and turns into a barcode. Dark lines, bright lines, sharp features at exact wavelengths. Hydrogen, oxygen, carbon, each leaves a chemical fingerprint. Shift that entire fingerprint toward the red, and the amount of shift tells you exactly how fast that galaxy is receding and how far back in time you are looking. A simple image, even from the most powerful spacecraft, is flat. Two coordinates, up, down, left, right on the sky, add a spectroscopic redshift, and suddenly every point gains a third coordinate, depth. Now, each galaxy is not just a dot, it is a location in three-dimensional space embedded in an expanding cosmic web. Map millions of those points, and a pattern emerges. No one expects a random spray. Instead, filaments, walls, and clusters appear, separated by vast cosmic voids. The universe looks less like static noise and more like a frozen, wind-shaped network. Here is where James Webb changes the rules. Hubble's vision cuts off before the deepest infrared, so the most distant, highest redshift galaxies slide out of view, their light stretched beyond its reach. They are there, but effectively invisible. Webb was engineered to see beyond that boundary into wavelengths where the earliest galaxies now live. Suddenly, regions that looked nearly empty become crowded with faint, red embers of primeval systems. But there is a harder question lurking behind all of this. It's one thing to map the bright, obvious galaxies. How do you chart the barely glowing dwarfs hiding in the background and the invisible dark matter scaffolding that holds the entire structure together? No one predicts that a narrow, deep field could expose that hidden framework. Yet Webb's deepest surveys are designed to do exactly that. In the next section, those tiny patches of sky turn into the most detailed 3D maps of the early universe ever made, and the hidden structure they reveal does not behave the way the standard script says it should. To pull off that kind of cartography, you need more than a pretty space telescope. You need a machine that can turn the faintest whispers of ancient light into a precise, navigable map of space and time. That is what James Webb was built to do. Before we get started, fix one image in your mind. A flower of gold, 6.5 meters across, hanging 1.5 million kilometers from Earth at a gravitational balancing point called L2. Those 18 hexagonal segments act as one mirror, gathering over 6 times more light than Hubble and feeding it to instruments so cold they operate just a few degrees above absolute zero. Designed to study the infrared universe, Webb is not just another observatory, it is an infrared cartographer. Its main cameras, NIRCam and NIR spec, are tuned to wavelengths where the earliest galaxies now glow. Light that left those systems when the universe was a few 100 million years old has been stretched by cosmic expansion, redshifted from energetic ultraviolet into the infrared bands that Webb was optimized to detect. That redshift is the first reason infrared matters. The second is dust. Interstellar dust that blocks visible light becomes translucent in the infrared, so Webb can see through the smoky veils where stars and galaxies are assembling. Regions that looked dim and opaque to earlier spacecraft suddenly reveal dense knots, filaments, and forming galaxies when viewed with Webb's longer wavelength eyes. Tonight, we're going to follow Webb into its deepest mode of operation. In deep field campaigns, the mission locks its gaze on one tiny patch of sky for tens of hours, sometimes more than a full day of total exposure time. Photon by photon, the signal accumulates. What looks empty to your eyes fills up with thousands of galaxies in a single frame, many so faint that no previous telescope in the solar system could have detected them at all. NIRCam provides those ultra-deep images, but NIRSpec turns them into something more powerful. By splitting the light from each galaxy into a spectrum, it measures precise redshifts, distance, velocity, age. Combine that spectroscopy with deep imaging and you do not just get a flat postcard of the early universe, you get a 3D map showing where each galaxy resides in space and when its light set out across the cosmic ocean. By the end of tonight, you're going to understand why this mapping matters. Programs like JADES in the goods fields, SEERS in the extended Groth strip, and Cosmos Webb over a much wider region are not just taking pretty pictures. They are systematic surveys stitching together overlapping deep fields into the most detailed atlas of the young universe ever assembled. No one expects a map to argue back. Yet, as these surveys sharpen, the structures they reveal are starting to push against the standard script, and the next section is where those quiet tensions explode into view. Those quiet tensions start with a deceptively simple question. How do you turn a flat image of space into a 3D map of the universe? To get depth, you need distance. To get distance, you need spectra. And to get spectra from the faintest galaxies that have ever existed, you need a survey strategy that is almost architectural. Now, let's begin with the deepest bricks in that structure. JD's, the JWST Advanced Deep Extragalactic Survey, is Webb's ultra-deep dive. Instead of sweeping huge swaths of sky, it stares into tiny, carefully chosen fields in regions like Goods South and Goods North, piling up exposure after exposure. The goal is ruthless. Catch galaxies that are so faint, so stretched by cosmic expansion, that their light has been on the road since the first few 100 million years after the Big Bang. In those JD's fields, scientists push out to redshifts greater than 10, even flirting with candidates beyond 13. Every spectrum pins a galaxy to a precise distance, turning a single pixel smear into a dot on a 3D grid. One by one, those dots begin to outline the earliest known building blocks of the cosmic web, tiny knots of matter that will someday grow into vast clusters of galaxies. But if JD's is the microscope, CEER's is the wide-angle lens. The Cosmic Evolution Early Release Science Survey spreads Webb's gaze over a larger patch in the extended Groth strip, not as deep, but far broader. That compromise is deliberate. By stepping back just a little, CEER's becomes ideal for catching the first hints of structure, filaments of galaxies, early walls, and proto-clusters stretching tens of millions of light-years across the young cosmos. Here the mission is to watch how those early knots connect. Spectroscopy again provides depth. Redshift after redshift transforms a 2D sprinkling of galaxies into elongated chains and clumps, revealing where gravity has already started to sculpt the invisible dark matter scaffolding that surrounds the entire solar system and extends far beyond. Then comes Cosmos Webb, the real survey hammer. Instead of going ultra-deep, it goes very wide, thousands of square arc-minutes over the famous Cosmos field. It is shallower than JD's, but it covers a slice of sky large enough to capture the statistical layout of the universe. How common different galaxy masses are, how often rare, massive systems appear, how the cosmic web's filaments, nodes and voids are distributed on truly grand scales. Together, these three strategies interlock: deep, medium, and wide, microscopic detail, architectural structure, and global pattern. By the end of tonight, you're going to understand that this is how scientists try to see both the tiny bricks and the entire cosmic city. No one expects a single survey to do it all. Each one fills a different layer of the 3D map. But when those layers were finally stacked, when JD's faint dwarfs, CEER's filaments, and Cosmos Webb's vast statistics were combined into a single evolving volume, no one predicts what emerged. The early Webb was not gentle, not tentative, and absolutely no one anticipates the hidden structure that appears next. To see why that hidden structure is so shocking, you have to rewind to the mental map scientists thought they were refining, not replacing. Before we get started with what Webb actually discovered, it helps to understand the quiet, orderly universe that LCDM said should be there. LCDM is short for Lambda Cold Dark Matter. Lambda is dark energy, the mysterious pressure driving the accelerated expansion of space itself. Cold dark matter is a slow-moving, invisible mass that barely interacts with light but dominates gravity. In this picture, dark energy sets the global expansion, cold dark matter provides the gravitational scaffold, and normal matter, the atoms in planets, stars and spacecraft, falls into that scaffold to build the cosmic web. Now, let's begin with the starting conditions. Roll the clock back to about 380,000 years after the Big Bang, when the universe cooled enough for light to travel freely. The cosmic microwave background is a snapshot of that moment. It looks almost perfectly smooth. The temperature varies by only 1 part in 100,000. Those tiny ripples in brightness are tiny ripples in density. Seeds where gravity can very slowly start to pull material together. In LCDM, that slow pull writes the next 13.8 billion years. First, small clumps of cold, dark matter grow a little denser than their surroundings. Then they attract gas. The gas cools, forms the first stars, and those stars gather into the earliest dwarf galaxies. Simulations show a clear pattern. Small structures first, then mergers, then growth into larger and larger systems. Over hundreds of millions of years, these dwarfs link up along filaments of dark matter. Filaments intersect to form nodes. Nodes become groups, then clusters. After a few billion years, those clusters stretch into walls spanning hundreds of millions of light years. Only then does the cosmic web become bold and dramatic, a skeleton of the universe that even ground-based telescopes can trace. But in the first few 100 million years, the expectation is very different. The web should be there in principle, but only as a faint sketch. More like gentle ripples than towering walls, more like a mist of small halos than dense, city-sized galaxy clusters. In the standard timeline, the early universe is a place of beginnings, not a fully built metropolitan system of structure. By the end of tonight, you're going to understand why that matters. Because this was the quiet confidence cosmologists carried into the JWST era. LCDM worked, it matched the microwave background, it matched galaxy clustering at late times. No one expects a single new mission to overturn that. Tonight, we're going to see what happens when that expectation meets data. The prediction is a soft, emerging web. The observation in some regions looks more like a finished wall. And that contrast is where the real mystery begins. Now, let's begin. Take one of Webb's most famous deep surveys, CeERS, the Cosmic Evolution Early Release Science Field. On the raw image, it looks like a random spray of tiny galaxies, faint smudges scattered across a postage stamp of space. No pattern, no obvious boundary, just distant light frozen from a time when the solar system didn't even exist. But then scientists do something new. They don't just measure brightness, they measure distance. With Webb's infrared instruments, they turn colors into time. Galaxies that are more red-shifted are farther away, seen earlier in cosmic history. By the end of tonight, you're going to understand why that one step transforms a pretty picture into a 3D map. In CeERS, they assign each galaxy a redshift, 0, 1, 2, 3. Then they push deeper, 0, 5, 6, 7. They color code by distance and stack the data. What looked like noise suddenly snaps into structure. Dozens of galaxies, all at nearly the same redshift, light up in the same hue. They're not scattered, they're aligned. Stretching across tens of millions of light years, those points trace a single elongated feature, a filament, a cosmic thread. In Hubble images of the same region, that filament is invisible. Hubble sees some of the brighter galaxies, but the fainter ones disappear into the glare of the early universe. The line never emerges. To Hubble, it's a coincidence. To Webb, it's a spine. This is where expectation meets reality. Standard simulations of LCDM do predict a cosmic web at Z, 5 times 7, but it's supposed to be soft, low contrast, still assembling. What CeERS shows in this slice looks more mature. The density contrast is sharper, the filament is more coherent. No one predicts such a clean, well-defined strand this early, stitched together from so many galaxies already falling into the same gravitational channel, and without Webb's spectroscopy, it would remain hidden. On the sky, these galaxies sit on top of one another in 2 dimensions. Only their redshifts reveal that they occupy the same depth in space, the same era, the same flow of matter along an invisible dark matter scaffold. Without those redshifts, it's just a chance alignment. With them, it's a revealed bone in the universe's skeleton. This is the pattern interrupt. A tiny grain of sky, smaller than the moon's face, holds a structure that feels too organized for its age. Is this one lucky filament that Webb happened to catch, or a sign that the early universe is laced with hidden walls and threads we've been blind to? Because CeERS is only one field, and the next discovery suggests this is not an isolated surprise. Because CeERS is only one field, and the next discovery suggests this is not an isolated surprise. So how do you know this isn't just cosmic pareidolia, a trick of perspective in deep space? Before we get started on rewriting cosmology, astronomers do something very undramatic. They count, they sort. They build what is essentially a bar chart of the universe. Every galaxy in these James Webb surveys comes with a redshift. That redshift tells you how fast space is expanding between us and that galaxy, and therefore how far back in time you're looking. If galaxies are unrelated, their redshifts scatter smoothly, but when they live in the same filament or wall, they clump. You get sharp spikes in a redshift histogram, narrow peaks where dozens of galaxies share nearly identical values. That's the first clue that you're seeing a real structure, not a random alignment. Now, let's begin to think in 3 dimensions. By the end of tonight, you're going to understand why astronomers don't trust pretty pictures alone. They take those redshifts, combine them with positions on the sky, and plot each galaxy in 3D space. Suddenly, the flat image of a deep field inflates into a cosmic volume. If the pattern is chance, rotate that 3D map, and it falls apart into a spray of points. If it's real, something different happens. Long overdense threads stay intact. Tilt the view, slice it, zoom in. The same elongated spine of galaxies keeps appearing, stretching tens of millions of light years. Sears shows one. JD's and Cosmos Webb show others. No one expects a random catalogue of points to line up into the same coherent bridge from multiple angles. But astronomers don't stop at that looks convincing. They build fake universes, supercomputer simulations of the standard LCDM model, generate billions of dark matter particles, then grow galaxies on top. From those, scientists draw random catalogues that preserve the survey's geometry and selection. Then they ask a hard question. How often does a filament this long, this dense, show up just by chance? In many of these Webb fields, the answer is almost never. The observed filaments and proto-walls are more extreme than what random alignments or even many standard simulations predict for such an early cosmic time. That tension is exactly what makes this new map of the universe so powerful. There is another trap: the way the mission looks at the sky. Selection effects can fake patterns. Maybe the survey is deeper in one stripe, or more sensitive to certain galaxies, or blocked by bright foreground objects. So teams carefully model the survey window, add those biases into their simulations, and then correct for them in the data. If a structure survives those corrections, it's far less likely to be an observational mirage. Tonight, we're going to follow that logic to its end. When redshift spikes, 3D maps, and statistical tests all point to the same filament or wall across independent instruments and surveys, astronomers start to see something else. The universe's true underlying architecture emerging from the noise. And once you trust the map, the next question is unavoidable. Why is that architecture appearing so early, and what does it say about the invisible matter and energy shaping everything? Once you ask why that architecture is appearing so early, Webb hands you the next surprise: crowded islands of galaxies that look like they arrived ahead of schedule. These are not gentle overdensities. They are the seeds of the most massive structures in the universe, showing up when the cosmic clock has barely started. Now, let's begin with what these objects actually are. A protocluster is the early, chaotic stage of a galaxy cluster. Not yet the smooth, relaxed city of galaxies seen in the nearby universe, but the construction zone. Dozens, eventually hundreds or thousands of galaxies all falling together into a shared dark matter well, all embedded in the same region of space that will, over billions of years, become a coma-like cluster, dominating its local volume. In the standard picture, these giants take time. Tiny fluctuations in the early universe grow under gravity. Small halos merge into bigger halos, then into clusters. It is a slow, hierarchical ladder from pebbles to boulders to mountains of matter. By the end of tonight, you're going to understand why that ladder suddenly looks too short. Webb's deep fields change the game. In surveys like JWST and CfA, scientists aimed the spacecraft at what seemed like empty space and let it stare. Out of that darkness, they reconstructed a 3D map at redshifts around 7 and beyond, less than 1 billion years after the Big Bang. And in those maps, they discovered something no one expects to see so clearly, so soon. Compact regions where dozens of galaxies crowd into a volume only a few million light-years across. One of these proto-clusters, at Z roughly 7, sits at a time when the universe is under 1 billion years old. Yet the galaxies inside already show substantial stellar mass, ongoing star formation, and signs of heavy elements forged in previous generations of stars. Designed models say this level of assembly should be rare. The observations say it is right there in front of the detector. Under standard LCDM, to build such a massive, dense node so quickly, the initial density fluctuations must have been unusually high. The dark matter must have collapsed with remarkable efficiency, or both. The prediction is gentle structure, slowly sharpening. The reality is sharp structure already in place. No one predicts proto-cluster cities lit up this early across multiple independent fields, and they are not isolated. These proto-clusters sit at the intersections of faint filaments, anchoring the emerging cosmic web. The hidden structure from the previous map is now populated. Cold gas flowing along dark matter scaffolding, feeding these nodes like rivers into a delta. What looked like a statistical hint becomes a physical, gravitationally bound environment. So, the tension grows. Are simulations underestimating how fast matter can clump under cosmic conditions? Is there something about dark matter's behavior or the physics of the very early universe that has been missed? Before we get started on the most extreme examples Webb has uncovered, there is one more twist in this hidden skeleton that pushes the entire cosmological model to its limits. That twist is this: most of the Webb was invisible. Hubble showed a universe filled with grand cities of stars. James Webb is now revealing that those cities sit inside a vast, hidden countryside of tiny, flickering lights that were almost completely missed. Designed to map the deep universe, Hubble's famous ultra-deep fields looked like the ultimate census, thousands of galaxies in a single frame, stretching back more than 13 billion years. But there was a catch. Hubble's vision picked out the bright tip of the iceberg, massive, vigorously star-forming galaxies, the cosmic capitals, the much smaller, much fainter dwarfs, the ones that actually dominate the head count, slipped under the detection boundary and vanished into the noise. Tonight, we're going to watch what happens when that boundary moves. Webb's mirrors collect more than 6 times the light Hubble could, and its infrared eyes see the stretched, reddened glow of very distant, very young galaxies. Suddenly, in those same patches of space, the dark gaps between the bright beacons are no longer empty. They fill with pinpricks, tiny, low-mass galaxies at redshifts of 8, 10, even beyond 12. In surveys like JWST and CfA, scientists zoom in on what used to look like isolated islands. With Webb, each island sprouts bridges. Chains of faint dwarfs trace delicate lines across the image, turning scattered points to continuous filaments. What looked like a sparse skeleton under Hubble becomes, under Webb, a richly veined system of arteries and capillaries, carrying gas and stars along the invisible dark matter frame. Prediction said the early universe should be relatively smooth on these scales. Observation now says otherwise. These faint galaxies sit along filaments like streetlights on a highway, marking where cold gas flows in and where future clusters of galaxies will grow. Their very existence in such numbers so early means the Webb was already sharply drawn when the universe was only a few 100 million years old. And they do more than mark the structure, they light it up. By the end of tonight, you're going to understand why many scientists now think these dwarfs were the real engines of cosmic reionization. Individually, each one is modest. Together, spread along filaments tens of millions of light-years long, they pour out enough ultraviolet light to strip electrons from hydrogen atoms and turn the foggy universe transparent. Add them into the 3D map, and the transformation is dramatic. The same volume that once looked like a loose scaffolding of bright galaxies now shows subfilaments, knots, and side branches that no one expects from the old surveys. No one predicts how much early clumpiness was being hidden. Absolutely no one anticipates that in some regions the number of faint galaxies outnumbers the bright ones by factors of tens or more. Which means those earlier maps were systematically biased. They were tracing the skyscrapers and missing most of the bricks, and when those bricks are put back in, something even stranger appears in Webb's deepest fields. Entire walls and megafilaments that seem too big, too early, for standard cosmology to explain. Those bricks do something no one expects. In one of Webb's deepest mosaics, they don't just form a vague overdensity or a fuzzy proto-cluster. They line up, they assemble into a razor-thin cosmic wall. Now let's begin. Imagine looking at a patch of sky so small you could block it with a grain of sand held at arm's length. In that speck, JWST's deep surveys, fields like Sears and Jades, don't just reveal a few bright beacons. They reveal hundreds of galaxies, many at redshifts between about 5 and 7, when the universe was less than 1 billion years old. On the sky, they trace a band. In 3 dimensions, they flatten into a sheet tens of millions of light-years across. This is the wall behind the deep field. It is not a solid surface, but a vast, planar arrangement of galaxies and dark matter, a kind of embryonic Sloan Great Wall glimpsed when the cosmic web is still young. From our perspective, it looks like a narrow stripe of galaxies, but when scientists measure their redshifts, something strange happens. The distances all cluster together. Dozens of galaxies that appear scattered on the sky occupy almost the same cosmic address. Redshift turns a flat image into a 3D map. By the end of tonight, you're going to understand why that matters. If those galaxies were randomly distributed, their redshifts would spread out smoothly with distance. Instead, Webb's spectroscopy shows a spike, a pileup of galaxies within a relatively thin slice of space, like a sheet of glass embedded in the early universe. The pattern interrupts expectations about how quickly structure should have grown from the nearly uniform plasma after the Big Bang. Closer to home, surveys like the Sloan Digital Sky Survey reveal giants such as the Sloan Great Wall, stretching more than 1 billion light-years across, and the Hercules Corona Borealis Great Wall, an even larger claimed structure in the local universe. Those were already pushing at the upper limits of what LCDM cosmology comfortably allows, but those appear after more than 10 billion years of gravitational growth. Seeing an analogue, scaled down, but clearly wall-like, when the universe is still in its first billion years, is a different challenge. LCDM does allow rare, large structures. Simulations produce filaments and sheets, and in the very largest volumes, they occasionally generate big, improbable walls. The problem here is the combination. The size of the structure, the density of galaxies packed into it, and the very early epoch at which it appears. Together, those push this wall toward the extreme tail of what standard models predict. Not impossible, but uncomfortably lucky. Before we get started on rewriting cosmology, caution is essential. Selection effects, lensing, and small survey volumes can exaggerate apparent walls. Yet, if this structure is not a fluke, if Webb keeps finding similar sheets behind other deep fields, then the universe did not wait patiently to assemble its skeleton. It started building at a breakneck pace. And the next structure Webb reveals may force scientists to redraw the entire cosmic blueprint. So are these early walls and filaments telling us the universe grew up too fast, or are we just staring at cosmic coincidences? Before we get started on rewriting cosmology, there's a quieter, more conservative argument. In a universe this huge, rare structures are not rare overall. Somewhere, the most extreme filament exists. Somewhere, the clumpiest region formed early. The concern is simple. What if Webb's deep fields just happen to land on those cosmic jackpots, and scientists are mistaking lottery wins for new physics? This is where cosmic variance comes in. Cosmic variance is the idea that what is seen in one small patch of space might not represent the universe as a whole. Point a telescope at a tiny pencil beam of sky, and that sightline might cut through an unusually dense knot of galaxies, or an unusually empty void. The underlying physics can be perfectly fine, but the sample is biased by local over- or under-densities. Deep surveys like JD's and SEER's are classic examples. They stare at areas so small that, on a full sky map, they would be invisible pinpricks. No one expects those narrow cones to average out the cosmic web. So when a massive protocluster appears at Redshift 7, or a filament stretching tens of millions of light-years shows up earlier than LCDM models predict, skeptics ask a fair question. Is this the rule of the early universe, or just a spectacular exception? Tonight, we're going to use a different kind of evidence: survey design itself. Programs like Cosmos Webb were built almost as an answer to this challenge. Instead of a tiny window, Cosmos Webb spreads Webb's gaze over a field nearly a square degree on the sky, mapping hundreds of thousands of galaxies. The goal is to average over many overdense and underdense regions to let the cosmic web's true pattern emerge beyond local quirks. And here's the pattern interrupt. When different teams, using different strategies in different directions on the sky, all start reporting early filaments, protoclusters, and embryonic walls, the coincidence argument gets weaker. One extreme structure could be a fluke. Two could be luck. But as JD's, SEER's, Cosmos Webb, and lensing selected fields all reveal overdense regions in the first billion years, the weight shifts. By the end of tonight, you're going to understand why many scientists now treat these signals as a real tension with standard models, not just statistical noise. Still, the door cannot close yet. No one predicts that first light surveys alone will settle this. Upcoming wide missions like Euclid and the Roman Space Telescope will map far larger volumes, track dark matter through gravitational lensing, and test whether Webb's clumpy early universe is typical or exceptional. The next question is unavoidable. Will those broader maps confirm that the cosmic web was already roaring to life, or reveal that Webb's first maps just happened to slice through a few extraordinary, improbable veins of structure? If those veins of structure were rare accidents, Webb should now fade into quieter territory. Instead, it runs into something even harder to explain. Overgrown galaxies in a baby universe that, by every standard calculation, shouldn't exist yet. These are not faint smudges barely hanging onto a few million suns worth of stars. Webb is picking up galaxies at redshifts greater than 10, less than 500 million years after the Big Bang, whose stellar masses rival, or even exceed, the Milky Way. In a cosmic nursery that young, some of these systems already look like fully stocked cities of stars. That is not what the standard growth charts predict. Under the usual rules, galaxies build up slowly. Dark matter collapses first, gas falls in, stars ignite, and over billions of years, mergers and inflows gradually assemble giants. When scientists run LCDM simulations with conservative star formation recipes, they get a universe where big galaxies emerge on long, patient timescales. No one expects a Milky Way's worth of stars to show up before the universe is even out of its cosmic infancy. Yet here they are. One candidate in the JWST survey at redshift around 13 appears to pack tens of billions of solar masses in stars just 320 million years after the Big Bang. Sears finds similarly hefty systems at redshift 10 to 12. To grow that fast, these galaxies would need to turn gas into stars with efficiencies that push against known physics, or live inside dark matter halos far denser than the standard model prefers. And their surroundings are a clue. These aren't lonely islands floating in empty space. Many of the most massive early galaxies sit in overdense regions, nodes where multiple filaments intersect, or embryonic clusters stretching tens of millions of light years across. The hidden scaffolding that Webb is mapping, those cold gas rivers and dark matter spines, seems to be funneling extraordinary amounts of material into a few privileged sites and slamming the accelerator on galaxy growth. By the end of tonight, you're going to understand why that makes cosmologists so uneasy. The first response is caution. Teams have gone back to remeasure these galaxies, checking redshifts, dust, and stellar populations. Some early masses do come down when assumptions are tweaked, but even after conservative revisions, a stubborn core of objects remains uncomfortably massive, still pressing hard against the upper limits of what the standard picture allows. So, what is this map really showing? Is dark matter clumping earlier or more strongly than expected, reshaping the boundary conditions for every later galaxy? Or are the recipes for star formation in the early universe simply wrong, hiding channels of rapid, dust-choked starbursts that previous telescopes could not see? No one predicts an easy answer, and absolutely no one anticipates that this is the last surprise Webb's hidden structure will deliver. Now, let's begin to follow those overgrown galaxies back to their roots, into the dark halos and invisible filaments that may be rewriting how cosmic history starts. Those roots are not made of stars, they're made of something you can't see. Something that outweighs every planet, every spacecraft, every glowing galaxy Webb has discovered. Tonight, we're going to walk along the universe's hidden skeleton, dark matter. On large scales, gravity is not run by the luminous part of the cosmos. It's dominated by this invisible mass that does not shine, does not absorb light, and does not care about the solar radiation or stellar winds blazing through the space. Dark matter clumps into vast halos, wraps itself around forming galaxies, and stretches into filaments tens of millions of light years long. Those halos and filaments act like scaffolding, setting the boundary lines where gas can cool, where stars can ignite, and where entire clusters of galaxies are allowed to grow. By the end of tonight, you're going to understand why astronomers say galaxies trace dark matter. The stars and gas are just the paint. The dark matter is the canvas underneath. Wherever this invisible mass piles up, its gravity pulls in hydrogen, compresses it, and lets galaxies take shape. When Webb maps an overdense region at redshift 7, or a chain of young galaxies less than 800 million years after the Big Bang, scientists are really seeing the bright frosting, outlining a much larger, unseen structure. But how do you map something that does not emit light at all? One answer is gravitational lensing. Mass bends space, and bent space bends light. A foreground cluster acts like a natural telescope, magnifying and distorting the images of background galaxies far beyond. No one expects those background galaxies to line up in perfect arcs by chance. Their stretched, sheared shapes are the imprint of dark matter's gravity. This is where Webb's sharp vision changes the game. Earlier missions could see the obvious: dramatic lenses, giant arcs, multiple images, mirrored galaxies. JWST sees the subtle ones: tiny shape distortions in thousands of faint background galaxies spread across deep fields like Sears and Cosmos Webb become a statistical map of where the mass really is, including the dark filaments threading between clusters. Before we get started on exotic new physics, notice what that means. Webb is not just taking a prettier picture of space, it is tracing invisible bridges of gravity. In some fields, those dark bridges line up with simulations of the cosmic web. In others, lensing hints at clumps and walls that seem to assemble too early or concentrate too much mass compared with standard models. No one predicts a perfect match, but absolutely no one anticipates how quickly tension is growing between lensing inferred structures and the neat LCDM simulations that have guided cosmology for decades. That tension is the crack in the skeleton. In the next section, those cracks widen as Webb's earliest galaxies begin to challenge what dark matter is and how fast the universe was allowed to build its hidden web. That crack in the skeleton is not just theoretical. In at least one place, Webb has caught the dark framework in the act. Stretching between two massive clusters like a hidden bridge. Designed as separate islands of gravity in earlier maps, they now look more like the towers of a single invisible suspension bridge. The system sits billions of light years away, a pair of galaxy clusters that earlier missions tagged as neighbors with possible interaction. Ground-based telescopes and even Hubble saw hints of something in between. A few distorted galaxies, a faint excess of X-ray emitting gas, a statistical nudge that there might be extra mass along the line connecting them. But the signal was muddy. The bridge was a rumor in the data, not a structure you could trace. Now, let's begin. Webb stares at the same region, this time in deep infrared, and the view changes. Suddenly, there are hundreds more background galaxies behind the pair, each one a tiny test particle in the gravitational field. Their shapes are not random. Along a narrow corridor between the clusters, those galaxies appear stretched, sheared, and subtly aligned, as if some unseen hand has combed their light in the same direction. Gravitational lensing turns that pattern into a map. Where the dark matter density is highest, the background galaxies are magnified and distorted the most. Scientists reconstruct the mass not from what glows, but from how space itself bends. In this system, the reconstruction reveals a filament, a continuous ridge of mass running from one cluster to the other, denser in the middle than the surrounding cosmic planes. It is not a vague overdensity. It is a bridge. Before we get started on what that means, look at what changed. Earlier surveys had a few dozen usable background sources. Webb's sharp vision and infrared reach pull in several times more, including very distant galaxies whose light left when the universe was less than a third of its current age. More galaxies means more constraints. More constraints mean the lensing solution tightens. A fuzzy hint hardens into a clean, high-contrast silhouette of dark matter. Tonight, we're going to see that this is exactly what simulations of the cosmic web predicted. In LCDM runs, massive clusters rarely sit alone. They grow where filaments intersect, connected by dark bridges that funnel in material like highways, feeding a city. But the timing matters. By the end of tonight, you're going to understand why seeing such a crisp, massive filament at this distance, and possibly this early, suggests the dark skeleton of the universe was fully wired sooner than many models expected. No one expects empty space between clusters to be truly empty. Yet no one predicts that a single observation could turn that emptiness into a visible, quantifiable structure. If one dark bridge can be mapped this clearly, how many more are quietly crisscrossing the early universe, setting the boundary lines where Webb's hidden galaxies will appear next? And what happens if the next bridge refuses to match the simulations at all? So here's the pattern break. When a dark bridge refuses to match the simulations, the first instinct is not tear up LCDM. It's what are we doing wrong? When a model has explained the expansion history of the universe, the distribution of galaxies, even the relic glow of the Big Bang, scientists do not throw it out lightly. Now, let's begin with humility. In this mission to redraw the map of space, the usual suspect is almost never the universe itself. It's the measurements, the assumptions, the way that faint smudges of light are turned into distances, ages, and masses. Before we get started on rewriting physics, the community asks a quieter question. Could these galaxies only look impossibly old and massive because the analysis is fooling us? One weak link is photometric redshifts. Webb often works by measuring brightness through a set of filters, then inferring how far the entire solar system has to look back in time. Change the dust content, tweak the star formation history, and the same colors can jump from a modest redshift to an extreme one. A galaxy that appears at 400 million years after the Big Bang might, with slightly different assumptions, slide to 800 million years, and suddenly look much less threatening to the standard model. Then there are stellar mass estimates. To turn light into mass, scientists must assume how many small, faint stars lurk beneath the glare of the bright, young ones. If those hidden stars are overestimated, the total mass inflates. Add uncertain dust corrections where a veil of interstellar grains can mimic an older, redder population, and the apparent titans of the early universe might shrink. Even selection biases cut in. Surveys like JWST and Sears are tuned to find luminous objects, so they naturally highlight the rare, extreme galaxies and miss the quieter majority. Tonight, we're going to follow what happens next, because the pattern is always the same. Headline results appear from photometry. Then the cross-checks arrive. Spectroscopic redshifts from NIR spec pin down precise distances by measuring individual emission lines. Independent teams rerun the data through different pipelines, changing priors, dust models, and star formation recipes. New surveys like Cosmos Webb look at wider patches of sky to test whether a claimed overdensity is a true cosmic structure or just a local statistical fluke. No one expects the first numbers to survive untouched. Early in Webb's mission, several galaxies in the Sears field were announced at extreme redshifts, apparently weighing in at more than 1 billion solar masses when the universe was only a few 100 million years old. With better spectroscopy, some of those redshifts dropped. The most shocking outliers softened. Yet even after the revisions, a core group remained uncomfortably massive and surprisingly evolved compared to LCDM expectations. Here's the balance that absolutely no one anticipates at the start. Careful scrutiny does trim the anomalies. Some walls fragment into smaller filaments, some proto-clusters dissolve into chance alignments. Some impossible galaxies move to safer redshifts. But they do not all go away. A persistent skeleton of early structures, dense regions and heavy galaxies survives every cross-check, holding the tension at the boundary between observation and theory, and setting up the next, harder question. If the model is mostly right, what, exactly, is it still missing? If the skeleton of early structure survives every test, then the missing piece has to be what runs through its veins, not just where the galaxies are, but how they are being fed. Tonight, we're going to follow something even more elusive than dark matter, invisible rivers of cold gas flowing along the Webb itself. Before we get started, rewind to the theoretical picture. In the young universe, simulations showed a counterintuitive trick. Instead of every galaxy sitting in a hot, shocked halo of gas, some regions should be threaded by relatively cool, dense streams funneled along dark matter filaments. These cold flows dive straight into growing galaxies, bypassing the usual heating, delivering fresh hydrogen like a direct pipeline from the cosmic background. On paper, it is elegant. In practice, it is almost impossible to see. The gas is too diffuse to glow brightly, too cold to light up like the blazing regions around massive black holes. For years, scientists had indirect hints from absorption in quasar spectra, but no one expects to just draw a clean map of these flows. No one predicts that a single space telescope could suddenly start tracing them in the first billion years. Then JWST turns on its spectrographs. Deep fields like Jades and Sears do not just catalogue faint galaxies, they slice their light into thousands of colours. In those spectra, narrow Lyman alpha emission lines appear, offset from the galaxies themselves, extended along the same directions as the underlying filaments. Absorption features in the ultraviolet show enormous reservoirs of neutral hydrogen and even cold molecular gas surrounding proto-clusters at redshifts 5, 7, and beyond. Expectation, isolated islands of star formation. Reality, galaxies drowning in supply. Some of the most overdense regions in Webb's map host star formation rates of hundreds of solar masses per year. That pace cannot be sustained by the gas already inside those galaxies. It demands a constant inflow, a river system feeding them from the larger cosmic web. Imagine the early universe as a dark continent. The filaments are valleys carved by invisible gravity. Along those valleys run rivers of cold gas, streaming at hundreds of kilometers per second. Galaxies sit like cities at the junctions where several rivers meet. The brighter the city, the more tributaries it taps, the more fuel it pulls from the web. By the end of tonight, you're going to understand why those cities light up so fast. This is not a static scaffold of matter. It is an active transport network, a circulatory system moving mass, momentum, and even metals around the young cosmos. The hidden structure is carrying a cosmic wind, channeling it into the densest nodes, accelerating the growth of massive galaxies and protoclusters far earlier than standard timelines prefer. And if these rivers are real, the next question is even sharper. What else is flowing along the Webb that current instruments can barely touch? If those rivers of cold gas are real, then James Webb has done something far more disruptive than draw prettier pictures of space. It has sketched a new map of the universe where the skeleton is already thick, already tangled, already busy, when standard timelines say it should still be thin and tentative. Now, let's begin. Step back and connect the pieces Webb has quietly laid on the table, early filaments stretching tens of millions of light-years at redshifts 5, 7, even higher. Proto-clusters packed with young galaxies that look like the seeds of modern galaxy clusters, but compressed into the universe's first billion years. Vast walls and sheets of galaxies like the bones of future superclusters, already traced out in deep fields such as JD's and Cosmos Webb. Layer on top the ultra-massive galaxies that no one predicts. Systems at redshift 10 and beyond, weighing in at tens of billions of solar masses when the cosmos is only a few 100 million years old. Dark bridges, hinted at by gravitational lensing, linking these dense nodes across what should have been relatively empty regions. And those cold gas flows, the hidden highways feeding the densest intersections of the Webb, turning on star formation like a switch. Taken one by one, each discovery is surprising. Together, they point to a deeper problem: clumpiness. In the standard LCDM picture, dark matter collapses first, slowly pulling normal matter into halos and filaments. On very large scales, the pattern is set by early quantum fluctuations, and LCDM nails that. The cosmic microwave background, the broad distribution of galaxies across billions of light-years, the overall expansion history, all of that still lines up with exquisite precision. But zoom in to small to intermediate scales, and the story gets uncomfortable. In many simulations, the early universe should look smoother than what Webb's seeing. Fewer massive halos, weaker filaments, less dramatic walls. The growth of structure should be more gradual, yet the spacecraft is finding overdense regions that feel like the universe hit fast forward. So is the model broken? Not in the sense of throwing out the entire framework. Tonight, we're going to stay in the regime where LCDM remains the most successful cosmological mission humanity has ever flown. But the details of how clumps grow, merge and light up may be off. The growth curve might be steeper. The timing of when halos cross critical thresholds might need to shift. In response, scientists are pushing every lever they can. They're tweaking parameters like the amplitude of primordial fluctuations and the exact behavior of feedback from stars and black holes, then running higher resolution simulations to see whether ordinary physics can catch up. Others are exploring more radical options: dark matter that is slightly warm or self-interacting, changing how quickly small structures form. Brief episodes of early dark energy that alter the expansion rate, even adjustments to inflation that seed extra power on certain scales. By the end of tonight, you're going to understand why this tension matters, because right now Webb's new map is forcing cosmologists to choose. Either the universe is telling us to refine a model that has passed every big test so far, or it's whispering that something deeper is missing. And the next hidden structure Webb uncovers may decide which path we take. So how big is this hidden structure, really? It sounds abstract until you put numbers on it, then it stops being a gentle bump in the cosmic web and starts to look like a continental plate in space. Now, let's begin. Start with the filaments Webb is tracing at redshifts 5, 7, even nudging toward 10. Some of these threads of galaxies and cold gas stretch for tens of millions of light years. The Milky Way is about 100,000 light years across. That means a single filament can be 300, 400, even 500 Milky Ways laid end to end. And that's just the spine, not the full region of influence around it. Around the knots where filaments intersect, Webb is finding proto-clusters, overdense regions that, in the modern universe, would grow into massive galaxy clusters. Their extents can reach 10 to 20 million light years. For comparison, the entire local group, including the Milky Way, Andromeda, and dozens of smaller galaxies, is only about 10 million light years across. So in a universe still in its cosmic childhood, some regions already rival or exceed the scale of our whole neighborhood. Then there are the walls. In some deep fields, the distribution of galaxies lines up along arcs and sheets, tens of millions of light years long, echoing the great walls and superclusters seen nearby, like the Sloan Great Wall or the Laniakea supercluster that hosts our solar system. No one expects to see baby versions of those continental-scale structures so clearly imprinted when the universe is only a few 100 million years old. This is where too big, too early comes in. The problem is not just absolute size, it is the combination of size, mass, and age, given the limited time available for gravity to amplify tiny primordial ripples into massive structures. In standard simulations, you do get rare extreme peaks, but they are needles in a haystack, not something you casually stumble across in multiple Webb fields. To feel that time pressure compressed the universe's 13.8 billion year history into a single human life, say 80 years. Redshift 10 corresponds to roughly 400 million years after the Big Bang, about 3% of the total age. On that scale, the universe at Redshift 10 is like a 2- or 3-year-old child. Finding a fully organized wall of galaxies there is like walking into a toddler's playroom and discovering a built-out megacity. Skyscrapers, highways, suburbs, all in place before kindergarten. Simulations within the LCDM framework do produce occasional proto-clusters and filaments at these epochs. Some scientists even predicted that a determined mission might glimpse the rarest peaks. But the apparent frequency, alignment, and maturity of the structures Webb has discovered may exceed those expectations. Prediction versus observation again. The model says extreme but ultra-rare. The data may be whispering common enough to find in a handful of pencil beam surveys. Before we get started on rewriting cosmology, though, there is a catch to know whether these structures really break the rules. It is not enough to count galaxies. Independent ways are needed to measure how lumpy the early universe truly was. That means mapping the invisible scaffolding itself, the dark matter, and the subtle distortions it imprints on the light that reaches our telescopes. Tonight, we're going to follow that trail, because the next step is to test Webb's hidden map against the universe's own gravitational handwriting and see which one blinks first. So Webb has drawn this intricate hidden skeleton of space. The obvious question is brutal and simple. Does the rest of the universe agree? By the end of tonight, you're going to understand that Webb's deep fields don't get to stand alone. They have to pass a lineup of independent cosmic witnesses. Now, let's begin. The first witness is gravitational lensing. When light from distant galaxies passes near massive structures, their gravity subtly stretches and shears the images. In weak lensing surveys, scientists don't look for dramatic Einstein rings. They measure tiny, statistical distortions in millions of galaxies, then reconstruct how all the matter, visible and dark, must be distributed to cause that pattern. It's like reading the wind from ripples on the surface of a lake. Here's the contrast. Webb's map is galaxy-based, bright tracers sitting on the dark matter scaffolding. Lensing maps are mass-based. They show the scaffolding itself. In regions where Webb's deep fields overlap with wide surveys from instruments like Subaru's Hyper Suprime Cam, cosmologists can ask a sharp question. Do the filaments, walls, and proto-clusters that Webb discovered line up with the peaks in the lensing mass maps? Or is there extra mass with no galaxies, or galaxies with no mass? No one expects a perfect one-to-one match, but large discrepancies would be a red flag. The second witness is older than every galaxy Webb can see, the cosmic microwave background. The CMB is the afterglow of the Big Bang, a nearly uniform bath of microwave light with temperature variations of only 1 part in 100,000. Those tiny hot and cold spots are the initial density fluctuations of the universe. Simulations take that pattern, evolve it forward under gravity, dark matter and dark energy, and predict how lumpy the cosmic web should be at every redshift. So any proposal that early structures grew faster or formed larger walls earlier has to rewind back to the CMB. Change the growth too much, and the simulation no longer reproduces that exquisitely measured microwave sky from Planck and WMAP. The boundary conditions are fixed. No one predicts that Webb can simply rewrite those without consequences. The third witness lives at intermediate times, large galaxy surveys. Projects like DESI are measuring precise redshifts for millions of galaxies, mapping the three-dimensional structure of the universe when it was a few billion years old. Future 21-centimeter experiments will trace neutral hydrogen across cosmic time, revealing where gas, and therefore future galaxies, were clustered. Together, they bridge the gap between Webb's infant universe and the relatively mature cosmic web seen today. These three witnesses enable consistency tests. Cosmologists compare how much structure growth Webb's early walls imply with how much growth is allowed by lensing and the CMB. If the same dark matter and dark energy parameters explain all three, the mission passes. If not, tensions arise and something in the system, observations, simulations, or the underlying physics, has to give. Before we get started on exotic new physics, there's one more twist. Upcoming observatories like Euclid and the Nancy Grace Roman Space Telescope will deliver enormous, sharp, wide-field lensing and galaxy maps. Webb sees tiny, deep pencil beams. Euclid and Roman will show whether those beams are typical neighborhoods of the universe or rare, overdense cities that absolutely no one anticipates. And if Webb's hidden structure turns out to be common, the next section will explore what that means for dark matter, dark energy, and the fate of the entire cosmic web. So, if Webb is showing you the crowded back alleys of the early universe, Euclid and Roman are about to step back and show the entire city. Not just one neighborhood, the whole cosmic metropolis. Now, let's begin. The Euclid mission, launched by ESA with major contributions from NASA, is built as a universe-scale surveyor. Its job is to map billions of galaxies across more than a third of the sky, turning the entire dome of space into a precise 3D chart of where matter lives and how it has grown. Instead of staring deeply at one pencil beam like Webb, Euclid sweeps wide again and again. The key is weak gravitational lensing and galaxy clustering. Tiny distortions in galaxy shapes reveal how invisible dark matter bends light, like a faint fingerprint of the cosmic web imprinted on every image. The way galaxies clump and cluster across hundreds of millions of light years tells scientists how fast structure has formed under the competing pulls of gravity and dark energy. By the end of tonight, you're going to understand that Euclid is less a camera and more a cosmic auditor, measuring how the universe's scaffolding has evolved over billions of years. If Euclid is the wide-angle inspector, NASA's Nancy Grace Roman Space Telescope is the ultra-precise accountant. Roman will deliver Hubble-quality imaging and spectroscopy, but over areas of sky hundreds of times larger than Hubble could cover in the same time. That means sharp views of faint galaxies, galaxy clusters, and the filaments between them, not in a few special fields, but across huge swaths of the cosmos. Roman will track how the expansion of the universe has accelerated, how dark energy has pushed on the large-scale structure, and how rare, massive systems, enormous clusters, gravitational lenses, and early collapsed giants are distributed across cosmic time. Designed to chase exoplanets and dark energy, it turns out to be perfectly tuned to hunt for the same kind of extreme, overdense regions that Webb has just discovered in miniature. Here is the contrast that matters. Webb zooms in deep on small areas, catching the earliest galaxies and hidden filaments in exquisite detail. Euclid and Roman zoom out, shallower but vastly wider, giving the statistical context Webb simply cannot reach. One shows the bricks, the others reveal the entire wall. If Webb's early clumpiness is real and common, Euclid's weak lensing maps should show matching overdensities, and Roman's wide, sharp surveys should find corresponding spikes in massive clusters and rare structures. If those signatures fail to appear, the tension with standard cosmology sharpens. No one predicts that outcome with comfort. Absolutely no one anticipates what it would mean for dark matter and dark energy. Tonight, we're going to treat the coming decade as a cosmic audit. Multiple independent spacecraft, multiple ways of weighing and mapping the universe, all cross-checking Webb's new map. But if all three agree that the universe grew its cosmic web too fast, the next section has to confront an uncomfortable question. Did something fundamental about gravity, dark matter, or even the Big Bang itself go beyond our current laws? So, if the cosmic audit says the Webb really did grow too fast, the next suspect on the list is unavoidable: dark matter itself. Tonight, we're going to walk right up to the invisible scaffolding of the universe and ask a slightly dangerous question. Not, what is dark matter, but could it be doing something it was never supposed to do? Before we get started, remember the standard picture. In the LCDM model, dark matter is cold, collisionless, and almost perfectly boring. Cold means the particles were moving slowly in the early universe, so they could clump on very small scales. Collisionless means they barely bump into each other and interact with normal matter only through gravity. Put those together and you get a very specific pattern. Tiny seeds collapse first, then merge into bigger halos, then link up into the filaments and walls that span hundreds of millions of light years. That recipe works astonishingly well. It matches the ripples in the cosmic microwave background. It reproduces the large-scale galaxy distribution, mapped by surveys on scales of hundreds of millions of light years. It even explains why the solar system orbits inside a massive dark halo that extends far beyond the visible disk of our galaxy. No one expects a single telescope, no matter how powerful, to overturn that entire system overnight. But Webb is poking at the margins. In some deep fields, scientists are seeing proto-clusters and filaments at redshifts 5, 7, even higher, already stretching tens of millions of light-years across space. Structures that in pure cold, dark matter simulations usually take more cosmic time to assemble. So theorists are asking, what if dark matter is still dark, still dominant, but not quite as cold, not quite as collisionless as the simplest version claims? Now, let's begin to explore the alternatives. Warm dark matter imagines particles with a little more thermal motion early on. They erase the very tiniest clumps, but can subtly change when the first mid-sized halos form. Self-interacting dark matter lets particles occasionally scatter off each other, redistributing mass inside halos and along filaments. There are even models where dark matter starts to clump unusually early, perhaps through interactions with a hidden dark radiation sector that never talks to light at all. Pattern interrupt. What if the hidden structure Webb discovered isn't a glitch in the map, but a fingerprint of those interactions? Slightly stickier dark matter could help overdense regions pull together faster, feeding gas into galaxies more efficiently, and building up the skeleton of the cosmic web earlier than plain LCDM predicts. But there is a hard boundary. Any tweak has to thread a needle. It must keep the exquisite CMB pattern intact, preserve the success of large-scale structure surveys, and still explain galaxy rotation curves and gravitational lensing. That's why no one predicts a wild anything-goes overhaul. The changes have to be subtle, almost surgical. By the end of tonight, you're going to understand one crucial point. Webb alone cannot tell which dark matter recipe is right. It can flag that our current ingredients might be missing a spice, but not what that spice is. To figure that out, the next section has to follow the gravity itself and see how space bends around this hidden structure. So if changing the dark matter recipe is one lever, there's another, even more dramatic dial on the cosmic control panel. You can change the expansion of space itself. When the universe stretches faster, gravity has less time to pull matter together. Slow that stretch, even briefly, and structures can grow that have no business existing so early. This is the tug-of-war that shapes everything Webb is now mapping. On one side, gravity tries to amplify tiny overdensities into galaxies, filaments, and walls. On the other, the global expansion of the universe pulls everything apart, thinning the cosmic medium and freezing growth. Change the expansion rate, and you change the score of that contest. How quickly galaxies assemble, how massive they can become, and how soon a hidden structure shows up in a deep field. Tonight, we're going to push that idea to its limit. Imagine the early universe not as a smooth, predictable balloon, but as a balloon whose inflation rate briefly stutters, faster, slower, then back to normal. That kind of hiccup leaves scars in the cosmic web. It can make some regions denser sooner, and that's exactly the kind of pattern Webb's new map is hinting at. One proposal that has exploded into the discussion is called early dark energy. In the standard picture, dark energy only dominates the expansion in the last few billion years, driving the present-day acceleration. Early dark energy suggests that, for a short window, much closer to the Big Bang, something with dark energy-like pressure briefly took over. It would have altered the expansion rate, changing how quickly those first overdensities could grow into the proto-clusters and filaments that Webb now sees at redshifts 5, 7, even beyond. The contrast is sharp. In the usual LCDM model, the early universe is radiation-dominated, then matter-dominated, with a smooth handoff to dark energy late in the game. Add an early dark energy bump and the timing shifts. Structures can either be suppressed or enhanced depending on exactly when and how strong that bump is. No one expects a huge, obvious spike. The changes have to be subtle enough that the cosmic microwave background and galaxy surveys do not immediately rule them out. Then there is inflation, the original hyper-expansion. During that ultra-brief epoch, quantum fluctuations were stretched from microscopic scales to cosmic scales, seeding the primordial pattern of over- and underdensities. Tweaks to the inflationary potential change the spectrum of those fluctuations. Slightly more power on certain scales, a gentle running of the spectral index, a small departure from perfect Gaussian randomness, and you suddenly get more, or larger, early overdensities. The scaffolding for a massive wall of galaxies at a time when the universe is still young. Here's the twist. These ideas were already on the table for a different problem, the Hubble tension. Local measurements of the expansion rate and early universe inferences from the microwave background disagree. Early dark energy and some inflationary tweaks were proposed to reconcile them. Now, Webb's hidden structures add a new constraint. Any modified expansion history has to fix the Hubble tension and simultaneously reproduce this unexpected abundance of early filaments without breaking the exquisitely precise microwave background data. Before we get started rewriting cosmic history, there's a warning. These models are speculative. They live on the edge of what current data allows. Webb's map is a clue, not a confession from the universe. No one predicts that a single exotic ingredient will neatly solve every tension. Every proposed change to early expansion must be run through the gauntlet. Cosmic microwave background, baryon acoustic oscillations, lensing maps, galaxy clustering, and now this new 3D skeleton that Webb has discovered. By the end of tonight, you're going to understand why that makes the next step so critical. If the expansion history is being questioned, the cleanest way to test it is not just to count galaxies, but to watch how space itself bends. In the next section, the mission shifts from drawing maps of where the matter is to using gravitational lensing to weigh it directly, and to see whether the hidden structure really demands a new kind of early universe. If you want to see theory under pressure, this is it. Webb's new map doesn't just reveal a hidden structure in space, it throws down a direct challenge to the digital universes running on supercomputers right now. For years, simulations like Illustrious TNG and UCHU have been the workhorses of modern cosmology. They start with a nearly smooth early universe, sprinkle in quantum-seeded fluctuations, then follow billions of particles of dark matter and gas as gravity pulls them into filaments, walls, and clusters from the Big Bang to the present. In those virtual universes, the cosmic web grows slowly. Galaxies assemble over billions of years, and massive clusters only lock into place relatively late. Now, let's begin. When JWST stares at deep fields like JADES, SEERS, and Cosmos Webb and finds sprawling protoclusters and thick filaments less than 1 billion years after the Big Bang, the comparison is immediate. Do those same patterns appear in the simulations at the same cosmic time, with the same intensity? Or has the standard LCDM picture of dark matter and dark energy missed something essential about how structure forms and how the solar neighborhood fits into the larger web? Simulators respond the way experimental engineers on a mission respond when a spacecraft behaves strangely. They don't throw the design away. They open the toolbox. They adjust cosmological parameters within allowed ranges, increase resolution so that one particle in the code represents less mass, and add more detailed physics, gas cooling, star formation, supernova, and black hole feedback, and radiation that can heat and strip gas from young galaxies. Every new Webb data release is another constraint, forcing these ingredients to be tuned so that the virtual universe and the observed one line up. Tonight, we're going to focus on one crucial twist: JWST-inspired tweaks. Teams now run targeted simulations of early massive galaxies that shine at redshifts above 10, of protoclusters stretching tens of millions of light-years at redshift 5 to 7, and of the faint filaments of cold gas that seem to feed them. The question is not just whether such structures can appear, but how often and in what kind of cosmic environment. If only standard physics and dark matter are allowed. Early results are tantalizing. In some high-resolution runs, massive early galaxies do form, and dense knots that resemble Webb's protoclusters emerge. But they tend to live in rare, extreme regions or require very aggressive feedback and finely tuned star formation efficiencies. The boundary between plausible outlier and impossible under LCDM is exactly where the debate now lives. By the end of tonight, you're going to understand that this is a feedback loop, not a crisis. Webb's map doesn't just break models, it guides them, forcing theory to become sharper, more predictive, and more honest about its uncertainties. And as the next step turns to gravitational lensing to weigh the hidden structure directly, simulators will have to answer a new, harder question. Can their universes bend light in exactly the same way that ours does? Gravitational lensing tells you where the mass is, redshift tells you when it is. Put those together, and suddenly this hidden structure isn't just a weird wall of galaxies. It's a timeline. Tonight, we're going to turn that timeline into a story your brain can actually hold. Before we get started, reframe one idea. Redshift is not just a number on a plot. Moving from low redshift to high redshift is like scrolling backward through a cosmic time lapse. Nearby galaxies at redshift 0.5 are late chapters. Redshift 5, 7, 10 are earlier pages when the universe was a fraction of its current age and the solar system did not even exist. By the end of tonight, you're going to understand that every point on Webb's map is also a moment. Now, let's begin. Imagine diving into a single JWST deep field, one of those JADES or SEERS images packed with faint smudges. At first, you float among the nearer galaxies a few billion light-years away. Big spirals, massive ellipticals, clusters where the cosmic web has already thickened, where the invisible dark matter skeleton has pulled in gas and lit up thousands of suns per galaxy. This is the mature city. Then you nudge the redshift slider higher. The nearest galaxies fade. New, smaller systems pop into view, groups that were single bright nodes split into multiple tiny galaxies stretched along narrow filaments. You are watching the web unwind in time. Those compact knots that looked like one city block at low redshift resolve into scattered villages connected by thin, dim roads of gas and dark matter. Push back further to redshift 7, 8, 10. No one expects much structure here. Simulations predict a relatively smooth universe, a few isolated proto-galaxies just learning to shine. But Webb's map shows something else. Filaments are already present. Proto-clusters tens of millions of light-years across are gathering. The web is fainter, yes, but it refuses to disappear. Now comes the pattern interrupt. Reverse the direction. Instead of moving backward, run the time lapse forward in your head. Tiny galaxy groups drift together and merge. Filaments that were hair-thin at high redshift thicken into glowing highways. Nodes brighten as more galaxies ignite, as supernovae and black holes pump energy into the surrounding space. The hidden structure grows the way a city grows, from a few scattered settlements linked by dirt tracks into a sprawling metropolis threaded with multi-lane highways and ring roads. This is not a static picture of space. It is a construction history. Scientists can trace how the boundary lines of those early overdense regions evolve, how the dark matter scaffolding channels cold gas along the filaments, feeding the planets and stars that will eventually form. No one predicts that a single JWST field would contain enough detail to follow that growth, yet that is exactly what has been discovered. Webb's new map lets you see the universe not as a frozen web, but as an unfolding mission of assembly. And as the next section turns from this grand time lapse to the most shocking individual structures inside it, the question becomes unavoidable. If the skeleton grew this fast, what else is hiding in its earliest bones? But before those individual oddities take center stage, there's a hard truth to face. Webb's breathtaking map is not the universe, it's a keyhole view through an almost unimaginably large door. Cosmos Webb feels enormous on paper, half a square degree of sky, stitched together into a single survey. Yet the entire celestial sphere is about 41,000 square degrees. That means this flagship field, the one revealing hidden filaments and early walls of galaxies, covers roughly 1/80,000th of the sky. The famous deep fields are even narrower, pencil beams drilled straight through space, tracing single, thin corridors across the cosmic web. Expectation, a grand atlas of the whole universe. Reality, a handful of ultra-detailed test patches. Tonight, we're going to stay honest about what that means. When only a few lines are drawn across a page, no one predicts that every mountain, valley, and ocean has been captured. The same is true here. A single line of sight can slice right through a rare, ultra-massive structure, or miss it entirely. That leads to the second limit, depth versus area. To see galaxies at redshift 10 and beyond, the mission has to stare for tens of hours at one tiny region. Go deeper, and the image sharpens in time. But it shrinks in space. Go wider, and you gain territory, but lose the faintest, earliest systems. By the end of tonight, you're going to understand why this trade-off matters. If an overdense wall happens to lie in one field, scientists might think such structures are common. If it falls between fields, they might conclude the early universe is smoother than it really is. Even inside those precious windows, the map is not drawn in ink. It's sketched in probabilities. Redshifts estimated from colors can be off, moving a galaxy tens or hundreds of millions of light years along the line of sight. Masses rely on how bright a galaxy is, how much dust it holds, how its stars are distributed. Change the assumed stellar population or dust content, and the inferred mass of a too big, too early galaxy can shift dramatically. Selection effects creep in as well. Brighter, bluer, easier to spot systems dominate the catalogue, while red, dusty, or ultra-diffuse galaxies slip under the detection threshold, and beneath all of it hides something Webb cannot see at all. The true cosmic web is woven from dark matter. Its filaments do not glow. The mission traces them indirectly, through the galaxies clinging to that invisible scaffolding, and through tiny gravitational lensing distortions in background light. No one expects a direct photograph of the dark skeleton itself. What is seen are the lanterns hanging on its beams and the way their light is bent by unseen mass. Now, let's begin to place this in perspective. Webb's new map is the best three-dimensional portrait of the early universe ever assembled. Yet it is still a first draft. Patchy, with blank regions, fuzzy distances, and uncertain weights. It shows that the standard picture may be under pressure, but it does not yet deliver the final verdict. Future spacecraft and missions, Euclid, Roman, even next-generation X-ray and radio observatories will have to widen the canvas, sharpen the measurements, and trace the dark web more directly. And that brings the story back to those shocking individual structures. If this is what appears in a few narrow beams through space, what happens when the surveys widen, the statistics harden, and the cosmic skeleton is mapped in full relief? Suddenly, that question is unavoidable. If a few pencil-thin beams through space already reveal walls, filaments, and crowded knots of galaxies, then the old picture of structure in the universe has to change. The classic story is simple. The early universe is smooth, almost perfectly uniform, with only tiny ripples in density. Over billions of years, gravity amplifies those ripples, drawing matter into a web of clusters, filaments, and vast empty voids. Smooth first, web later. That is the expectation. Webb's map does not erase that story, it complicates it. In deep fields like JD's and Sears, scientists are seeing a surprisingly articulated skeleton at redshifts 7, 8, even beyond 10, when the universe is less than 500 million years old. Protoclusters spanning tens of millions of light years, filaments of galaxies threading between them. No one predicts this level of organization so early, yet there it is, glowing in infrared. To make sense of it, the word structure has to stretch. It can no longer just mean the grandest walls and the richest clusters. It has to include the entire hierarchy. Tiny dark matter halos, individual galaxies, the filaments that feed them, and the diffuse gas flows that run along those filaments like rivers. Tonight, we're going to treat the cosmic web less as a single object and more as a nested system of scales. On the smaller scales, clumps form fast. Slight overdensities in dark matter collapse first, creating halos that can host the earliest galaxies. Those halos merge, stack, and grow. On intermediate scales, chains of halos align along invisible dark matter strands, pulling in cold gas and guiding it toward future clusters. Only on the very largest scales do the most massive superclusters and walls fully emerge, a process that can take several billion years. So, when Webb reveals a protocluster at redshift 7, that does not mean the entire cosmic web is finished. It means the first rungs of the ladder are in place far earlier than models preferred. Early structure now depends on which rung is under discussion: halos, filaments, or the colossal superstructures they eventually build. Cosmologists are already adapting their language. Instead of asking, "When did the web turn on?" they are splitting the question, "When did the first halos appear? When did coherent filaments channel gas and galaxies? When did those filaments knit into the fully mature network mapped at low redshift by surveys like Sloan?" By the end of tonight, you're going to understand why that distinction matters for dark matter, dark energy, and even inflation. This is not theory chasing observations from behind. Models are being rerun with different initial conditions, different dark matter properties, different feedback from early stars and black holes. Some simulations can grow early knots and filaments like those Webb has discovered, but often only in rare regions. or with parameters pushed to their limits. No one expects the tension to vanish overnight. For you as a viewer, this is a quiet upgrade in how to see the universe. Instead of a simple, smooth, then clumpy timeline, think in layers. A hidden scaffold of dark matter, a mesh of filaments carrying gas like a galactic wind, galaxies lighting up along those threads, and enormous superstructures still assembling over billions of years. Now, let's begin to use that layered view on one of Webb's most controversial finds, a single, colossal structure that seems to jump several steps up that ladder far earlier than it has any right to exist. That impossible wall Webb sees isn't just a curiosity in deep space, it's the opening chapter in a story that ends with planets, oceans, and observers asking where it all came from. Before we get started, zoom back in your mind from that colossal structure to the invisible architecture beneath it. Those early filaments and protoclusters are not random clumps. They are regions where the dark matter scaffold is slightly denser, where gravity pulls in more gas, where the cosmic web tightens its grip. Over hundreds of millions of years, those threads funnel material into knots. Knots become proto-galaxies. Proto-galaxies collide, merge, and ignite. Tonight, we're going to follow that chain. In those crowded nodes, stars form fast and die young. Massive stars fuse hydrogen into heavier elements, explode as supernovae, and hurl carbon, oxygen, silicon, and iron back into the surrounding medium. Each generation seeds the next. The universe starts almost pure hydrogen and helium. By the time galaxies have crashed together a few times along a filament, their gas is enriched enough to build rocky planets and complex chemistry. Webb's hidden structures are the conveyor belts that make that enrichment possible. By the end of tonight, you're going to understand that our own Milky Way is not floating alone in space. It sits on one of these filaments, a modest river of galaxies feeding into a much larger basin. That basin is called the Laniakea supercluster, a gravitational watershed spanning hundreds of millions of light years. The Milky Way orbits within a small group, the local group, which itself flows along the filament toward a massive node known as the Great Attractor. Our entire solar system is embedded in that motion, carried along by a cosmic wind of galaxies sliding down the Webb's gravitational slopes. No one expects the local address of a galaxy to matter for life, but environment shapes history. A galaxy parked in a dense node might grow quickly, undergo violent mergers, and host frequent supernovae and active black holes. Great for rapid chemical enrichment, terrible for long-term planetary stability. A galaxy adrift near a void might evolve slowly, with fewer heavy elements and fewer planets, but also fewer catastrophic events. Filaments, like the one cradling the Milky Way, sit in between. Enough interaction to build metals, not so much that every young solar system is constantly reset. This is where contingency enters. The hidden structure Webb is mapping is not just background scenery, it is part of a causal chain. The density of a filament billions of light years away affects when certain galaxies form, how fast they enrich their gas, when they can host stable planetary systems, and ultimately whether there is time for biology to emerge and wonder about its origins. Now, let's begin to imagine the emotional scale of this. When Webb stares into a deep field and reveals a faint, thread-like alignment of tiny red smudges, those are not just distant galaxies, they are ancestors. Some will merge into future spirals and ellipticals, some will form planets that never cool enough for life. Others may, after tens of billions of years, host oceans under alien suns. picture a civilization far down one of those filaments, looking back. Their spacecraft cross the boundary of their heliosphere. Their scientists map their own cosmic web. They discover that their galaxy, too, rides a filament in some vast supercluster, and absolutely no one anticipates the moment they realize that the barely visible structure in Webb's map was, for us, the first clue to their existence. Because Webb's controversial wall is not the only structure out there that shouldn't exist, the next one may force us to question something even deeper. So, what happens when a map like that lands on the desks of working scientists? No one expects the universe to politely fit their equations forever, but absolutely no one anticipates how fast a single telescope can make decades of confidence feel provisional. The first wave hits in 2022. Webb's deep fields come back from missions like SEERS and JDS, and within months preprints appear claiming galaxies at redshift 10, 12, even 13 that look impossibly massive. Designed to trace the faintest smudges of light, this spacecraft suddenly seems to be finding full-grown cities, where the standard model says there should only be tiny villages. Headlines shout that cosmology is broken. Some astronomers quietly wonder if the solar system's favorite theory of structure formation just missed something fundamental. Then the pivot begins. Not in a dramatic press conference, but in long, careful sessions at conferences and workshops. In small rooms at Cosmos Webb meetings, in late-night Zoom calls comparing catalogues, teams line up their measurements of the same galaxies and the same filaments. Are the redshifts photometric or spectroscopic? Are the stellar masses inflated because dust, metallicity, or lensing were mismodeled? By the end of tonight, you're going to understand that this is where the real drama happens. Not in the first claim, but in the relentless recheck. Pattern interrupt. The story is not Webb killed LCDM. The story is that the community refuses to let one exciting map redraw the entire universe without a fight. Healthy skepticism becomes the background wind. Cosmologists know that LCDM has survived precision tests of the cosmic microwave background, galaxy clustering, and gravitational lensing. They also know that every model, no matter how successful, has a boundary where it starts to creak. So they treat Webb's hidden structures as both opportunity and threat. If those early walls and filaments are real, the mission has discovered a crack in the foundations. If they're not, the system is working as designed. Slowly, views update. Some of the most dramatic, impossibly massive galaxies shrink when better spectroscopy nails down their distances and compositions. A few candidates move to lower redshift, becoming merely impressive instead of impossible. But other anomalies refuse to vanish. Overdense regions at redshift 5 to 7 keep showing up in independent surveys. Proto-clusters spanning tens of millions of light-years reappear in different fields, with different instruments, analyzed by different teams. Now, let's begin to see the pattern. Claims are made, challenged, and either eroded or reinforced by new data. Review papers synthesize dozens of individual results, weighing which tensions remain after the dust settles. Before we get started on rewriting any textbooks, the community insists on this cycle. Tonight, we're going to watch that cycle continue. Because Webb's new map is not finished, and neither is the process of deciding which hidden structures will survive to reshape our cosmic story. So where exactly does this hidden skeleton begin? At what point in cosmic history can you say, here, this is where the Webb turns on? Tonight, we're going to pin that down, not with a single line in time, but with a series of milestones. Now, Let's begin with the first, not quite, Webb. Picture the universe a few 100,000 years after the Big Bang. On a horizontal timeline in your mind, that's the first big marker, the cosmic microwave background at redshift Z D1100. The plasma cools, atoms form, light can finally travel. The map from that era shows only tiny temperature ripples, 1 part in 100,000. These are not filaments, they're the seeds. The first nonlinear clumps grow out of them at redshifts around Z1 30 tan 20. Tens of millions of years later, when dark matter overdensities start collapsing faster than the cosmic expansion can tear them apart, slide your mental pointer rightward. By the time redshift falls to Z since 15 to 10, around 500 million years after the Big Bang, those clumps begin to link up. This is the era of the first stars and small galaxies, the moment when gravity starts drawing matter into thin bridges between nodes. No one predicts clean, dramatic filaments yet. Simulations show wispy, low-contrast strands of gas and dark matter. But this is the first recognizable scaffolding. Webb's deep surveys are dropping us right into that transition zone. JD's, Sears, Cosmos, Webb. These are not just pretty images of space, they are 3D slices along that timeline. At redshifts 7 to 5, roughly 800 to 1200 million years after the Big Bang, scientists are now finding filaments tens of millions of light years long and proto-clusters packed with young galaxies. What should have been subtle hints are coming through as clearly defined structures. The boundary between isolated clumps and coherent web has been pushed earlier. Extend that mental graphic further. Mark Z 3-1 as the age of large walls and mature proto-clusters, hundreds of millions of light years across, the ancestors of today's superclusters. Then, all the way at the right edge of the axis, redshift 0, the present-day cosmic web mapped by surveys like SDSS. Before Webb, many textbooks quietly placed the Webb Begins Here label near ZM 3-4, where large-scale structure becomes obvious in older data. By the end of tonight, you're going to understand why that label has to move. Webb has effectively shifted the marker to much higher redshift, into an era when absolutely no one anticipates such elaborate structure. The universe's hidden skeleton was already in place, already channeling gas and dark matter along invisible filaments, long before planets, solar systems, or even most galaxies existed. And that forces a new question. If the Webb is older than expected, what does that say about the way our entire cosmological model was built? That question sounds dramatic, but it does not mean the universe is broken. It means the picture is sharpening. The same way Voyager didn't overthrow gravity when it pushed through the heliopause, Webb's new map doesn't erase a century of cosmology. Gravity still pulls. General relativity still predicts how space curves. The cosmic microwave background still glows at 2.7 Kelvin, matching a hot Big Bang. The broad arc of history, from fireball to plasma to atoms to galaxies, still holds. What changes is the fine print, the timing, the efficiency, the way structure condenses out of that expanding fireball. The standard LCDM model says small clumps of dark matter form first, then slowly merge into filaments, walls, and clusters over billions of years. Yet in Webb's deep fields, scientists are seeing filaments and proto-clusters tens of millions of light years across when the universe is only a few 100 million years old. Same rules, same cosmic game, just playing faster and more aggressively than the simulations predicted. This is not the first time space has done this. No one expects the universe in 1998 to suddenly demand dark energy. But distant supernovae fade too quickly, and the only way to reconcile them with the cosmic microwave background and galaxy surveys is to add a new ingredient, a repulsive component that accelerates expansion. The old framework survives, but with a shocking twist. A similar story plays out with neutrino masses. They were once treated as weightless. Then oscillation experiments prove they have mass, and cosmology quietly updates the ledger while keeping the main structure intact. Tonight, we're going to treat Webb's hidden skeleton the same way, not as a demolition order, but as a renovation. The mission is revealing ultra-massive early galaxies, overdense knots along filaments, and walls that form earlier than expected. That does not mean dark matter vanishes or dark energy evaporates. It might mean dark matter interacts a little differently, or that inflation left slightly stronger ripples in the early universe than the simplest models assumed. By the end of tonight, you're going to understand that these tensions are not a crisis. They are coordinates pointing toward the next version of the model. Before we get started on those possibilities, pause on what this tension really signals. When predictions and observations line up too perfectly, it can mean the data are shallow. The solar wind, the heliopause, the shape of the heliosphere, those only became strange once spacecraft actually reached the boundary. In the same way, Webb is finally pushing cosmology into a regime where no one predicts every detail correctly. That is exactly where progress happens. So in a few years, cosmologists may look back on these deep fields the way planetary scientists look back on the first Voyager images of Jupiter's moons. The moment the universe stopped being smooth theory and started showing scars, fractures, and hidden architecture. The moment it became stranger, but still recognizably ours. And the next step is to test whether this intricate skeleton is real, using every lens, spectrum, and survey that can be launched into space. So now, step back and look at what just happened to your view of space. A few minutes ago, the universe was a flat wallpaper of galaxies. Now it's a living three-dimensional system of filaments, walls, and nodes, evolving in time, shaped by invisible dark matter and the slow, relentless wind of cosmic gas flows. Before we get started on the next mysteries, lock this in. Those JWST deep fields, JADES, SEERS, Cosmos, Webb, are not just pretty star fields. They are slices through space-time. Each redshift is a different era. Each faint smudge is a tracer particle in a vast experiment, revealing where the dark scaffolding pulls matter into threads, where those threads knot into proto-clusters, and where great empty voids open up in between. By the end of tonight, you're going to understand that 4 core ideas run through everything. First, JWST's deep fields reveal hidden structures far earlier than expected. Filaments and walls already stretching tens of millions of light-years across, when the universe was less than 1 billion years old. Second, the real skeleton is faint. Tiny galaxies barely above the noise and cold hydrogen gas glowing in infrared emission outline a secret framework that older telescopes almost completely missed. Third, some of those early structures simply grow too fast. Prediction versus observation is stark here. Models of LCDM cosmology say large-scale structure should emerge gradually, but JWST has discovered overdense regions and massive galaxies at redshifts greater than 10 that look more like mature cities than construction sites. No one expects skyscrapers in a village, yet there they are, shimmering in the early universe. Fourth, this map is not finished. Future missions like Euclid and the Nancy Grace Roman Space Telescope will cross-check it with gravitational lensing, precision spectroscopy, and huge surveys, either tightening the current picture or forcing a redraw. Here is a trick to keep all of this alive in your head. Whenever a deep field image appears, a tiny patch of sky crammed with galaxies, imagine color-coding every galaxy by distance. Cool blues for the nearby universe, greens and yellows as you move out, deep reds for the earliest systems. Now mentally rotate that image. Watch as those colors separate into filaments, as clusters pop out in 3D, as blank regions reveal themselves as vast, cosmic voids. You're no longer looking at a flat photograph. You're watching the cosmic web light up. That shift means something. Tonight, we're going to treat you the way scientists treat each other. As someone who now thinks like a cosmologist, you see beyond the 2D sky, you see underlying architecture, the hidden boundary lines of dark matter and dark energy that tell the universe where to grow. And this new mental map is not just for this one mission. The next time a headline mentions a puzzling early black hole, a strange dark matter signal, or a new measurement of cosmic expansion, you'll know where to place it, on a filament, in a node, or out in a void. Because the real surprise is still coming when one of those pieces refuses to fit on the map at all. Because the real surprise is still coming when one of those pieces refuses to fit on the map at all. Now, zoom out. Imagine standing with early ocean navigators on the edge of a continent, holding the first truly accurate chart of a coastline. The shore is no longer a rumour. The bays, the capes, the dangerous shoals are inked in, but the interior, the mountains, the rivers, the hidden cities, those are still blank. Tonight we're going to stand on that same kind of boundary, except the coastline is the observable universe. For centuries, scientists drew their own versions of that shoreline. From the first hints that the Milky Way is one galaxy among many, to the realization that space itself is expanding, each generation added a rough line, a better estimate, a new equation. Then, piece by piece, technology caught up with imagination. Radio dishes, CCD cameras, orbiting observatories, infrared detectors cooled to a whisper above absolute zero. Layer by layer, a chain of inventions, theories, and international collaboration built a single, quiet spacecraft, parked 1 million miles from Earth, at a gravitational balance point staring back into time. Now, let's begin to appreciate what that actually means. This one telescope is calmly redrawing the entire large-scale map of reality. Deep field surveys like JD's, SEER's, and Cosmos Webb are not just pretty images, they are 3D atlases of structure when the universe was less than 1 billion years old. They show filaments, walls, and protoclusters already stretching across tens of millions of light years, in an era when standard models predicted something much smoother, much less organized. No one expects a colossal skeleton to show up there. No one predicts that between the bright galaxies, a hidden lattice of cold gas, dark matter, and faint, previously invisible galaxies would glow just enough in Webb's infrared eyes to give itself away. Yet that is what these maps reveal, a cosmic web that was always present but only now becomes legible. The universe had bones long before earlier telescopes could see them. Think about the time scales involved, light leaving those early filaments set out when the cosmos was a few 100 million years old. It has been travelling for more than 13 billion years through expanding space, crossing the evolving solar system, slipping past planets and dust and magnetic fields, only to be focused onto gold-plated mirrors and turned into data. By the end of tonight, you're going to understand that those faint photons are not just signals, They are coordinates on a new kind of map. From this vantage point, the contrast is almost dizzying. Primitive structure there, precision instruments here, a young universe weaving its first strands of gravity, and a late-arriving species using that same gravity as a tool to weigh invisible matter and trace invisible threads. The mission is no longer just to count galaxies, but to read their arrangement as a sentence in a language written by dark matter, dark energy, and the primordial wind of inflation. So this is the image to hold on to. The universe as a vast, evolving web, filaments as highways, clusters as city lights, voids as dark oceans between. A map still wet with new ink, with entire regions yet to be charted, and right now you are standing on the coastline, watching the first accurate contours appear, as the story of space written in light and gravity finally begins to read itself to us. So, if this is the coastline, and Webb has just sketched the first true outline of the continent, the question becomes simple. Do you want to keep walking inland? Because that is what engagement actually does on a channel like this. A like is not just a quick tap, it is a small signal that says, yes, keep pushing into the dark. A comment is not just a reaction, it is data that lets long, complex missions like a 2-hour dive into cosmology survive in an algorithm tuned for 10-second clips. A subscription is a quiet contract that says, when the next map arrives from deep space, you want to be there when it unfolds. Before we get started on that next chapter, there is a request. Leave a comment with the region of Webb's hidden structure that hit you hardest. Was it the impossible-looking wall of galaxies 10 billion light-years away, stitched along a filament that should not exist yet? Was it the early, overdense knots where no one predicts such massive galaxy clusters so soon after the Big Bang? Or was it the realization that the darkest voids on the map are not empty at all, but threaded with cold gas and dark matter scaffolding Hubble never fully saw? Then push the map forward, say what you want to see charted next. Should the next long-form mission follow the invisible rivers of dark energy that are stretching this entire system apart? Should it dive into the Hubble tension, where two different ways of measuring the expansion of space disagree so sharply that absolutely no one anticipates both can be right? Or should the focus shift to exoplanet systems, using Webb's spectra to draw weather maps on worlds orbiting other planets' suns? Because tonight, we're going to treat this video as only one entry in a field notebook. There are already journeys waiting that track dark matter experiments hunting for the particles that might be holding this whole cosmic web in place. There are episodes on Euclid's first wide maps of the sky showing the same filaments on scales Webb cannot reach, and on how future missions will use gravitational lensing to weigh those hidden structures, one warped galaxy at a time. Here is the pattern interrupt. This is not just entertainment. Nearly 2 hours spent here is a real resource. It tells scientists, communicators, and the invisible recommendation systems that there is an audience for careful, high-effort tours through the deep structure of space. So if someone in your life loves space but still thinks the universe's map was finished with Hubble, send this to them. Let them see that the boundary lines are moving, that by the end of tonight you're going to understand how provisional every atlas of the cosmos really is. Thank you for walking this far into the new map. Stay subscribed, stay curious, and this channel will be back with the next contour, the next anomaly, the next piece of the universe's evolving web drawn in sharper light. Before we get started on the next anomaly, take a detour. Imagine you're not just looking at Webb's deep fields, you're reading them. Tonight, We're going to turn those pretty wallpapers into navigational charts of the early universe. Now, let's begin with color. JWST sees infrared light far beyond what human eyes can detect, so scientists assign visible colors to different filters. A shorter wavelength infrared filter might be mapped to blue, a medium one to green, a longer one to red. The result looks natural to you, but it's a code. In a deep field, like jades or seers, the bluest specks tend to be closer, shining through less cosmic dust. The reddest smudges are often two things at once: dust obscured and stretched by the expansion of space, their light pulled to longer wavelengths as it travels billions of years. That's why, in these fields, red doesn't just mean pretty, it often means ancient. A tiny crimson arc near a foreground galaxy might be a system at redshift 10, seen when the universe was under 500 million years old. Some of those red islands are candidates for galaxies that standard models never expected to be that massive, that early, but the colors are only the surface. Behind every point of light there's a catalogue entry. Astronomers overlay grids of detections on these images, each source tagged with position, brightness in every filter, and an estimated redshift. On a screen in a mission control room, the same JWST deep field you see on social media can be covered in circles and labels. What looks like a star field becomes a spreadsheet on the sky, a 3D map where each dot has a distance, a mass estimate, even a star formation rate. Those distances come in two main flavors. Photometric redshifts use the brightness pattern across multiple filters to guess how far the light has been stretched. They're fast. They work for tens of thousands of galaxies at once, but each one carries uncertainty. Maybe 10 to 20%, sometimes worse for very faint, very red objects. Spectroscopic redshifts come from spreading a galaxy's light into a spectrum and measuring the precise shift of known lines. They're slower, more expensive in telescope time, but far more exact. Early structure maps use spectroscopy to anchor the scale, then photometry to fill in the web between those anchor points. Try a mental exercise. Pick a random thumbnail of a JWST deep field online. Now choose a tiny square patch in the corner, no bigger than a grain of sand at arm's length. In that patch, count the obvious galaxies, the bright spirals, the fuzzy ovals, the tiny red embers. Then imagine stacking them by color. The bluish ones sit in the nearer universe, maybe a few billion light-years away. The golden and orange ones trace intermediate distances. The deepest reds stretch far beyond, some over 10 billion light-years out, lying along filaments and walls that no one predicts in such strength that early. You're not just looking at a flat picture. You're looking down a tunnel through space and time, past our solar system, through the foreground planets and stars, out into the scaffolding, where the first great structures condensed from dark matter and gas. By the end of tonight, you're going to understand that this isn't passive. With this toolkit, color as code, catalogs as coordinates, redshifts as depth, you can pull up any JWST deep field and see more than beauty. You can see the hidden skeleton of the universe, the same emerging map that has scientists quietly asking what else the cosmic web is hiding beyond the edge of our current models. Now, let's begin to pull on a dangerous thread. You've just seen how James Webb turns a pretty deep field into a 3D map of filaments, knots, and voids. But what if that hidden skeleton had come out differently? Change the web, and you change everything that can ever happen inside it. Imagine a smoother universe. Same Big Bang, same expanding space, but the tiny initial ripples in density are weaker. The dark matter scaffolding is there, yet its filaments are thinner. its intersections less crowded. Protoclusters like the ones JWST sees at Redshift 7 are rare, not common. Galaxies take longer to collapse. Stars ignite more slowly, spread out across a gentler cosmic landscape. In that universe, the first bright galaxies that Webb now detects at Redshift 10 might not appear until Redshift 5 or 4. The cosmic dawn is delayed by hundreds of millions of years. Fewer supernovae enrich the gas. Fewer heavy elements mean fewer rocky planets. The whole solar system story is pushed back, or maybe never quite gets going at all. A smoother Webb looks peaceful, but it could be a universe where the lights turn on too late for complex chemistry to fully exploit the available time. Now flip the dial the other way. Picture a more violent universe where those primordial ripples are stronger and gravity grabs harder, earlier. Filaments collapse fast. Intersections become crushingly dense. No one expects structure to assemble this quickly, but in this scenario, protoclusters make the ones JWST has discovered look tame. Galaxies slam together in rapid-fire mergers. Black holes grow like weeds. In that cosmos, the sky over a young planet would be spectacular and lethal. More quasars, more gamma-ray bursts, more tidal shredding as galaxies plunge through each other's halos. Planetary systems near the crowded filaments might be torn apart before stable orbits can settle. The same Webb that feeds galaxies becomes a gravitational blender, hostile to long, quiet epochs where biology can slowly experiment. Some scientists use this kind of thought experiment in a careful, almost surgical way. They ask how different histories of structure formation might change the odds that observers ever arise, not as a mystical answer, but as a boundary condition. Out of all the possible universes with slightly different early physics, which ones actually grow long-lived stars, metals, and planets that survive the cosmic weather? Here's the unsettling part. Tiny changes in the initial conditions or in the behavior of dark matter and dark energy ripple forward into enormous differences in the Webb. When filaments form, how thick they are, how violently they feed galaxies. Small tweaks at the beginning, radically different outcomes billions of years later. And yet, this is the version that happened. This particular hidden structure, this balance between smooth and violent, is the one that led to a universe where a solar system can quietly orbit inside a filament and build instruments to map its own origins. Tonight, we're going to follow Webb as it tests whether that balance truly matches our theories, or whether the next layer of the map reveals something no one predicts. That balance between smooth and violent gives you something powerful, a map. But the universe itself is not the map, it is the territory. And even a telescope like Webb, drawing filaments and walls out of darkness, is still giving you a model of a reality no instrument can touch directly. Before we get started wrapping this up, hold that in mind. Every glowing point in a deep field, every measured redshift, every reconstructed 3D filament is an inference. Light travels through expanding space, through intervening gas, through dark matter scaffolding. Scientists correct, calibrate, and deconvolve. By the end of tonight, you're going to understand that what looks like a photograph is really a carefully argued claim about what the territory must be. A few decades ago, that territory looked almost blank. The first maps of the early universe showed a nearly featureless haze. No one predicts intricate filaments at Redshift 10 or protoclusters tens of millions of light-years across when the cosmos is only a few 100 million years old. The expectation is a smooth young universe. The reality revealed by this mission is a Webb that assembles faster, earlier, and with stranger knots than models were comfortable with. Designed to see faint galaxies beyond Hubble's reach, Webb's deep surveys redraw that region completely. Where there was once a vague patch labelled too early, too distant, there is now a crowded landscape, overdense walls, hidden structures in cold gas, galaxies whose masses push the limits of standard timelines. The boundary between what is known and what is guessed has moved, but it has not disappeared. That is the crucial point. This map will not be the last. As new spectra come in, as gravitational lensing measurements refine the invisible skeleton of dark matter, as Euclid and Roman trace the cosmic web on even larger scales, the lines will shift. Some impossible structures will dissolve under better data. Others will sharpen into undeniable features. The map gets closer to the territory but never becomes it. And you are not just watching this from a distance. By learning how these maps are drawn, how predictions about the solar system or the large-scale structure of space can fail, and how spacecraft and telescopes push past each old boundary, you become part of the process. You help decide which anomalies are noise and which demand that the entire picture be redrawn. Now, let's begin the quiet part. Somewhere in those deep fields, in the noise Webb filters out, there are patterns no one expects, alignments absolutely no one anticipates, structures that do not fit any current simulation are already hiding in the data stream. The next version of the map is on its way, carried on the wind of photons that left their galaxies before planets like this one even existed. And when that new map arrives, the territory will still be waiting, larger, stranger, and just beyond the edge of what we can see.